introduce cumulative distribution function, probability density function, and expected value. Next, we'll be looking at the continuous random variable families. Specifically, we'll be studying Gaussian random variable. Finally, we conclude with mixed random variables. A random variable x is continuous if the range Sx consists of one or more intervals. CDF is defined, as you see here, with this formula for any random variable, continuous random variable x. And here, note that this small x refers to the values of the random variable x. Here is the properties of CDF. CDF is 0 when the argument becomes -infinity, and it becomes 1 when the argument becomes infinity. And the probability that any random variable x is in between x1 and x2 is simply the difference of the CDF values at x2 and x1. Here, how we see a CDF, as you see, it always starts from 0 and goes to 1. So it's a function defined between 0 to 1, but it's an increasing function. A continuous random variable then can be simply defined based on this CDF concept. If we have a continuous CDF, then that random variable is continuous random variable. Probability density function. Probability density function is simply the derivative of CDF. Okay, so if you want to get the PDF, we take integral of CDF. I'm sorry, CDF is integral of PDF, and PDF is derivative of CDF. Okay, it's you see, usually it has a peak value at the points where the random variable takes the highest number of occurrences. Here we see in example 4.3 a modem voltage. Suppose that we measure the voltage of the signal in a modem. We'll see that most of the values that we measure will be either 5 volt or -5 volt. Due to the noise or other disturbances, we might have some values close to 5 volt, but the number of 5 volts, if we make an experiment, collect the data, and then measure the voltage, the most of the values will be 5 volt. So simply, PDF shows us the highest probable values of a random variable. For any continuous random variable, the PDF is a positive number for all x. Okay, it cannot be negative. The integral of PDF should be 1, which means that the area under the PDF is unity. And as we have already given in previous slide, the CDF can be derived from PDF through this integration. Next, if you want to determine the value of the random variable x between x1 and x2, So here, for example, here is my PDF. Okay. The area under this curve should be 1. And it's always positive. Okay. And we got the 2 values of the random variable. Let's say capital X. And we want to know probability that the random variable in between these 2 values. So we have to determine this area actually. So we simply take the integral of PDF over the range x1 to x2. Here's a quiz example. We are given a random variable x. Its PDF is in here. And it's cx e to the minus x over 2 for all x values, positive x values. Determine the constant c. To determine the constant, we have to use this identity, this property, integration of PDF must be equal to 1. So I can simply insert this into here and look at the range. The range is from 0 to infinity because x is greater than 0, so it might go to infinity. So we simply write it x e to the minus x over 2 dx, which is equal to 1. So since all of them are given, we can determine c here. Next, the CDF of fx. To find the CDF, we should use, we should use this formula. So the CDF of x should be integration of whatever the c here, we insert c here, cx e to the minus x over 2 dx over the range minus infinity to x. Okay, we can easily determine that. Next, probability that x is between 0 to 4. So to find this, we can integrate from 0 to 4 fx. Okay, which gives us probability that x is greater than or equal to 0, less than or equal to 4. Okay, similarly, we can determine this. As you see, in most of the questions here or examples here, you should use either integration or derivation. Expected value is another critical parameter of a random variable. The expected value of a continuous random variable is given by this formula. You see there's a factor x in here. And usually this integration is very straightforward. Here we have an example. Here is the PDF. And we want to find expected value of x. We simply integrate it. You see, over the 0 to 1, 0 to 1. We insert 1 times x, so x, which is 1.5 meters. Similarly, you can do this example from the textbook. Okay, families of continuous random variables. There are many random variables, either discrete or continuous. In this course, we selected some and studied them, especially those which are quite useful for electrical engineering. The first continuous random variable family is uniform random variable. Uniform random variable has this PDF. Okay, we can plot this PDF. Usually, it's simply given uniform A to B. So uniform over A to B. And let's draw it. Let's say this is the random variable values. And here is A, here is B. Then it's simply a rectangle whose amplitude is 1 over b minus a. So you see, if I look at the area here, the area of this curve, you see, it should be 1. So we simply integrate 1 over b minus a dx, sorry, b minus a from a to b dx, which is 1. Okay, this proves that the PDF is well defined. There is no ambiguity. Next, if we have such a uniform random variable, its CDF is given with this formula, which is simple, which starts from A to B again, A to B, 0 otherwise, so it goes to 0 in here, and after B it becomes 1. So here it is 1. So let's plot another curve here. So this should be fx of x, and this should be fx of x. Okay, over the same, over the same range. Now let's see here, when x is a, it's 0, right? When x is b, it is 1. So simply, it's an increasing function like this, a line. So this blue one represents CDF, and the red one represents the PDF of uniform random variable. Here's an example. Here we got the phase angle for the signal of a modem, and it's uniformly distributed. So theta is uniform over where? 0 to 2 pi. So 0 to 2 pi. And what's the PDF, CDF expected value and the variance of theta? For the PDF, as usual, we can simply write it. It's 1 over 2 pi. Remember that it was 1 over b minus a. So this is a, this is b. So it is between 0 to 2 pi. Sorry, again, I don't know what's happening, but 0 to 2 pi, and otherwise it's 0. For the CDF, as usual, we just add it. Okay, can you hear me?
Yes.
Can you hear me?
Yes.
Okay, good. So the 0 when theta is less than or equal to 0, and theta over 2 pi between 0 to x. Sorry, theta. It should be theta right here. This should be theta. Okay, theta. I don't know what's happening here. Theta 2 pi when theta is greater than 2 pi, that's 1. Okay, so for the expected value, we should use the integration. Remember that it was fx of x dx. Through the range 0 to 2 pi. So we just take this integration 0 to 2 pi, I'm sorry, this should be x here. So theta, right, x, fx is 1 over 2 pi d theta, which is pi. And the variance, by the way, of theta is expectation of theta minus mu theta squared. Okay, we have already described this in previous lesson. Next, exponential random variable. It has this PDF where lambda is greater than 0. Okay. And Erlang random variable, it has two parameters, n and lambda. So Erlang and lambda, whose PDF is given with this formula. It's a little bit complicated. Here lambda is a positive number and n is an integer starting from 1. And for an Erlang random variable, expected value is given in terms of n and lambda, and the variance is given in terms of n and lambda again. And Poisson random variable, the next one, it's given by this PDF. You see, it's a little bit complicated. And finally, the Gaussian random variable, which is one of the most important random variable in electrical engineering and in others, some other disciplines. The Gaussian PDF has this form, and we use this representation, Gaussian mu sigma, where mu is the mean value and sigma is the standard deviation. Okay, here is two plots of this PDF. Here the mean value, you see the curves are symmetrical at the center. Here the center is mu, which is 2, and mu again 2, and standard deviation here is 0.5, here it's 2. So mu is the center of this random variable, I mean the PDF, the center of the PDF, and sigma simply defines the width of this curve, how much it's spread over the range of the random variable. You see it's quite peak here. It has a peak which is around 0.8, while here it's, you see, spread and its peak is smaller. This is always like that because the area of this and this should be equal. Okay, equal area, and it is 1 based on the axioms of probability. You remember the integration of PDF simply is 1. Okay, then this should be 1. So whenever we see a very, spreaded Gaussian random variable, a PDF, then we simply think that the standard deviation is high. When it is sharp, then the standard deviation is low. If we got the Gaussian PDF of x, and if we define a new random variable, ax plus b, then the next random variable, the new random variable, is also Gaussian, but its mean value will be a mu plus b, and the standard deviation will be a sigma. Standard normal random variable, it's just a Gaussian random variable with mu and sigma. Here mu is 0 and sigma is 1. Then that's called normal, standard normal random variable. Standard normal CDF then is given with this formula. It's not easy to evaluate, so use table. We usually use tables to determine this phi phi z, and in the textbook you can find a table for phi z. So for any z, we see such a table. For every z value, we determine phi of z. For any Gaussian random variable x, the CDF can be written in terms of this phi, this function, by using this normalization. So we define a z, which is x minus mu over sigma. So probability that x is in the interval AB can be written with this as in terms of phi, as you see. And phi, how do we read this phi of z? It's simply, you see, determines the values of this from minus infinity to x. So phi z simply gives us the area of Gaussian PDF until z. So from minus infinity to z. Then we can define, since the area is unity, so we can define 1 minus phi of z as the area of here. Okay? The area here is going to 1 minus phi of z. So here it is. Then phi of minus z is 1 minus phi of z. Okay, here we have 3 examples. Let's do them. It's important. Suppose that user current test is x, which is 46. A sample value of Gaussian. Okay, here's the Gaussian. And here is mu, here is sigma. Okay, so the mu is 61. So you imagine that in your class, the mean value, the average of the test score is 61, and you got 46. So it's not good, right? The standard deviation is 10, and it's a random variable. Express your test score as a sample value of the standard random variable, normal random variable z. Okay, remember the formula. Z was simply x minus mu over sigma. So x is 46. So 46 minus the mu, the average value, which is 61, divided by the standard deviation 10, which is what? Which is minus 1.5. Okay. Next, we got the Gaussian random variable again. What is probability that the x, the random variable, is less than or equal to 46? Okay, probability that x is less than or equal to x was the CDF simply, right? So we can write this. X is less than or equal to 46 is going to be f x 46. Okay? And fx 46, you know, 46 was what? Z 46 minus 61 over 10, which is minus 1.5. So this one will be fx 46 will be simply phi minus 1.5, okay, which is z. So next we look at the table. Here's the table. I look at the number of z. Here there is no negative value. Then I should use another identity. Here it is. Phi minus z is equal to 1 minus phi c. Then phi minus 1.5 is going to be 1 minus phi 1.5. Okay, so we look at here. from the table and find the value of phi, and then find the value of fx46. Okay, which is 0.933. So the probability that you get 46 or less is 0.067. So it's about 6.7%. Okay, 6.7%. Next, we got the same Gaussian random variable. The mean value is 61. The standard deviation is 10. What is the probability that the random variable is greater than 51, less than 71? Okay, to determine this, remember that this was given just like A1, A2, or X1, X2, and it was simply a range over X1 to X2. We can use the previous slide again. Z was X minus mu over sigma. So we can determine this one and this one. This becomes then Z becomes then -1 to 1. Okay. And then the probability that the Z is in between that is simply given with phi of Z. So phi of Z minus phi of minus Z will give us the difference between two probability values. Standard normal complementary CDF, which is simply 1 minus phi of Z. So in the textbook, you will find two tables. One is phi of Z. The other one is Q of Z. And Q of Z is 1 minus phi of Z. So you can use both, either phi of Z or Q of Z. Here is an example. We got an optical fiber transmission system. Probability of a bit error is given in terms of this Q function, which is square root of gamma over 2, where gamma is the signal to noise ratio. What is the minimum value of gamma? So gamma minimum. To produce a bit error rate not exceeding 10 to the minus 6. So this is equal to 10 to the minus 6. What is gamma then? Okay, to find this, we have to look at the value of Q function at this. And here we can have a look at that. Here it is. You see this one, for example. This is approximately here, let's say. Okay, when, so QZ, let's see. When QZ is 4.75, it becomes 1.2, 10 to the minus 6. So it's approximately minus 6. Okay, now then this should be equal to, okay, gamma over 2 square root of 4.75. From here, then I can determine gamma, which is 45. Okay, so it should be greater than 45 so that the bit error rate should not exceed 10 to the minus 6. Okay. Next, let's see the unit step function, which is used in especially delta unit step function, Dirac delta function. Unit step function is defined as a number, as a function that starts from 0, goes to infinity. So we can draw it x 0 to infinity. So we can just make it a different color. So 0 Okay, here is 0, here is 1. So if we, for example, write ux minus 1, then this means that you shift this to the right by 1. So start from here. Let's use a different color again. Here is 1. So here it is. Okay? Or u, for example, x plus 1, then it's going to start from here, minus 1. Okay? So unit step function is equivalent to integration of direct delta function from minus infinity to x, or direct delta is the derivative of unit step function. So we got a close relationship between, okay, direct delta and unit step function. One is derived from the other. Okay, we have a PMF here and the CDF here. Okay, y takes on values 1, 2, 3 with equal probability, so each is 1 over 2. Then the PMF and the corresponding CDF of y can be written with this formula. Now we can write this CDF using unit step function, right? So let us draw it first. You see, before 1, let us determine here 1, 2, and 3, which is y. And we are drawing fy of y. Okay. So before 1, it's 0. Let us use a different color. Before 1, it is 0. And then at 1 to 2, it's 1 over 3. So 1 over 3 until 2. And then 2 to 3, it's 2 over 3. So 2 over 3. And then after 3, it is 1. Okay. So this is 0, this is 1. This is 1 over 3, 2 over 3. So here is my CDF. Now, how can I write this using unit step function? You see, unit step function looks like this. So I just get the summation of this. So 1 over 3, the magnitude is 1 over 3, u, y minus 1. So I got a unit step function starting at 1, whose amplitude is 1 over 3, plus, so the next unit step start from here, you see. Okay. So the magnitude is 2 over 3. So 2 over 3, u, y minus 2. Okay. Next, I got another one starting at 3, whose amplitude is 1. Okay. So, okay, this should be 1 over 3. I'm sorry. We have to add them up. So we add this. So 1 over 3. Again, 1 over 3, because we add them up. U, y minus 3. Okay. Now the PDF fy of y will be the derivative of this. And remember that the derivative of unit step function gives us direct delta. So then the PDF can be written in terms of direct delta, as you can see here. And here is how we plot the PMF. Here is the PMF. The CDF, we have already drawn that in previous slide. And then PDF. Okay, you see that's a mixed type random variable, and the expected value can be found from this formula, yfy of y, and since we got integration of direct delta, which gives us unity values. Okay, this is the end of the presentation. Do you have any question?
No.
Evet. Okay.